Hello and welcome to another Reigate Maths Further Maths video, Further Mechanics, and we're looking today at successive oblique impacts. Now what that means is when a particle or sphere of some sort hits one wall and then bounces off and hits another wall and bounces off that one. So we're really just going to apply what we've used before, but we've got to do it twice. So it's very important to have a clear diagram and be very clear in your mind and you're working exactly what you're doing. So we've got the initial angle is 40 degrees. It will come away as an angle of beta. So I tend to use alpha and then beta. Then when it collides with the second wall, if the two walls are perpendicular, like they are in this example, that angle there will be 90 minus beta. So to save having an extra variable, we're going to call that 90 minus beta, and it's going to come away with an angle of gamma. So I tend to always use those same letters. We're told that E is 0.6 between the sphere and both walls, wall 1 and wall 2. So we're going to look at each collision and see what's happening. We're going to get a lot of equations. We need to be very careful in our working. So let's have a look at how we can solve this problem. So for the first collision, we do need all the space for this example. So for the first collision, we're going to, so that's with wall 1. So parallel to the wall, I've got an unchanged velocity, so 3 cos 40 is equal to V cos beta. This is actually V here. That's V cos beta. So that's my first equation. Perpendicular to the wall, perpendicular to wall 1. I know that 3 sine of 40 multiplied by E, which is 0.6, is V sine of beta. And that's equation 2. I want to know the speed and the direction of motion. So I've got to solve for V and for beta. So doing equation 2 divided by equation 1, that gives me tan of beta is equal to 3 sine 40 times 0.6 divided by 3 cos 40. And that gives me 0.6 tan 40. And when I solve this for beta, I get that beta is 26.7 degrees. Finding the speed, we found the angle, but finding the speed, it's best to go back to our initial equations rather than just plug this in, because then we might be asked for an exact value. So just make sure you can do that. So we're going to do equation 2 squared plus equation 1 squared, and that gives me V squared, because we'll have B squared sine squared beta plus V squared cos squared beta is equal to 1.8, that's 3 times 0.6, sine 40, all of that squared, plus 3 cos 40, all of that squared, and that leads to V is 2.57 meters per second. We might not be asked to find it exactly, in which case we can just work like this. Now the second collision, let's see what's happening there. Second collision. That's with wall 2. So let's look what's happening parallel to wall 2. Now notice parallel to wall 2 is perpendicular to wall 1. So you have a lot of that sort of thing going on. But parallel to wall 2, we've got the V coming along here, and then we need to find the cos of 90 minus beta. And that's equal to W, this velocity, times the cos of gamma. So working that out, we get V. Now, cos of 90 minus beta is the same as the sine of beta is W cos gamma. But we know what V sine of beta is from up here. So from here, V sine of beta is 1.8 times sine of 40. So I've got 1.8 sine 40. That's what V sine beta is equal to from up here, is W cos gamma. And that is equation 3. So then I'm going to look perpendicular to wall 2. So perpendicular to wall 2, I've got V times the sine of 90 minus beta multiplied by E, which is 0.6, is equal to W sine of gamma. Just check we're right with that. So we've got V sine of 90 minus beta times 0.6 is W sine of gamma. So we've got those, that's perpendicular to the wall. So we're trying to get to the direction and motion after the collision. So let's just tidy this up as much as we can. That's going to give me 0.6. Now V, this is going to be V cos of beta is equal to W sine of gamma. Now we're happy for that to stay there, but can we do something better with this? Yes, we can. V cos of beta from up here is 3 cos 40. So I've got 1.8, because 3 times 1.6 is 1.8. Cos 40 is W sine of gamma. And that is going to be equation 4. So I've got equation 3 and equation 4, and then I'm going to divide those in the usual way. So we're going to do equation 4 divided by equation 3, gives me tan of gamma is equal to, now you need to be a bit careful here, 1.8 cos 40 over 1.8 sine 40. So now this is actually cot of 40. So when we work that out, work this all through, you will get that gamma is equal to 50 degrees. Working out equation 4 squared plus equation 3 squared, that leads to W squared is equal to 1.8 sine 40 squared plus 1.8 cos 40 squared, all squared, and that gives me that W is equal to 1.8. So we've solved the second part of the question. Now, a couple of things to notice here. The outgoing velocity, angle of velocity is 50 degrees. So looking back to the carefully drawn diagram, this is 50 degrees here. So if that's 50 degrees, that's 40 degrees, 90 minus, hold on a second. So that's 50 degrees there. That's telling us that these two velocities are parallel, because if you work around the angles from that, if we drew in this line here, that's 50 degrees there, and so that's 50 degrees. So it comes back parallel to its initial velocity, but only if E is the same for each wall and if the walls are at right angles, and you cannot just write that down. They often make the two walls have different coefficients of restitution, so then you can't do that. But that is an important thing to notice. And it's also true that the speed if E is the same and it's 90 degrees, will be, if you look here, the speed that it comes away at is E multiplied by the initial speed. But you can't just use that. However, you might be asked to show it in a question. Right, looking at the next question, which is very similar. We've got two smooth walls meeting at right angles on a smooth horizontal floor. The first particle comes along, bouncing off each wall in turn. The first collision is at 30 degrees to the wall, and we know the kinetic energy before this is 8 joules, and we know that E is 0.7. So we can't just write down the information that we found in the last question, we've got to work it through again. So the kinetic energy is a half mv squared. So they're just using that to test whether you know that, and we're going to use that to find out the approach velocity. So that's going to be a half times 1 times v squared, and we're told that that is equal to 8. So this gives me that v squared is 16, so v is 4. So that's where that 4 has come from. Now we've got to look at the first collision. So the first collision, we're going to go parallel to the first wall. So this is wall 1 and this is wall 2. So parallel to the first wall, I've got 4 cos 30 is equal to v cos beta, and perpendicular to the first wall, I've got 4 sine of 30 is v sine of beta, but of course we've got to multiply by e there, which is going to be 0.7. Got that? So that's 0.7 there. So we can solve these two equations here together. So this is equation 1 and this is equation 2. So dividing those through, I get equation 2 divided by equation 1 is tan of beta is equal to 0.7 times 4 sine 30 over 4 cos 30, and that gives me beta is equal to 22.0 degrees. So that's the angle that it comes off the first wall. We also need to find the speed. So we do that by squaring and adding, so that we've got the velocity squared is going to be 4 root 3 over 2 all squared. So that's going to be this one here, plus this is 1.4 because sine of 30 is a half, so that's 2, so that's 1.4 squared. So this leads to V being 3.736 meters per second. And then we need to write the answer. It moves after the first collision at 3.74 meters per second at an angle of 22 degrees to wall 1. Don't leave the person marking your work to find your answers. So that's part A. Part B, we need to find the kinetic energy of the sphere after the second collision. So let's look at the second collision and see what happens. So the second collision. Parallel to the wall, we've got the sine of, so this is going to be 90 minus beta. So this is V, parallel to the wall is V cos of 90 minus beta, which is sine of beta, is equal to W cos gamma. And then perpendicular to the wall, we've got 0.7 multiplied by V cos beta, because we're looking at sine of 90 minus beta, is equal to W sine of gamma. And working through these, we can work out what W squared is equal to. So W squared is going to be this squared plus this squared, and we've got some of these values up here. So you need to use as exact values as you can. So we've got that W squared is V squared sine squared beta plus 0.7 squared V squared cos squared beta. And this gives me W squared is equal to, and then working this out using the values up here that we found before, we're going to get 349 over 5 sine squared 22 degrees plus 0.49 cos squared 22 degrees, which is 7.839. That's what W squared is equal to. So we want the kinetic energy, which is a half W squared times 1, which gives me 3.92 joules. If you look at these two equations here, you can work backwards. You can say that W squared, by squaring and adding, is, let's just work it through. There's an option to work through using your initial values up here, which slightly simplifies the working and arguably makes it come out a little bit neater. So let's see, what we could use here is we can use that W cos gamma here, using that equation, is equal to V sine beta. And V sine beta up here is 2.8 sine 30. We've also got that W sine gamma is equal to 0.7 multiplied by V cos beta, which is here, for cos 30. We can then square and add these to get W squared is equal to 2.8 squared times sine squared 30 plus, that's 2.8 cos squared 30, and that gives me W squared is 2.8 squared. So the kinetic energy is going to be a half times 1 times 2.8 squared, and that gives me 3.92 joules. So that gives me the same answer, but you can see that we didn't have to use the 22, which is a more sort of fiddly number to use. What you can see from both of these examples is you get a lot of equations over the page. You need to set your work out very clearly, first collision, second collision, number your equations as you go so that you can refer back to what you're doing. You need to be very accurate in this, otherwise you end up with a silly error.